The next topic is semiconductor devices, diodes. So what is a PN junction diode? A diode is a circuit element. A diode is a circuit element that allows electric current to flow in only one direction, like one-way valve. That is, a diode is a circuit element that allows electric current to flow in only one direction. Now, how a PN junction diode is constructed? The PN junction diode is constructed from single piece of semiconductor that is doped so that one side is p-type and other side is n-type. So a PN junction diode is constructed from a single semiconductor that is doped so that one side is p-type and other side is n-type. This is the band diagram of a PN junction diode before equilibrium. This is the valence band which contains holes, and this is the conduction band which contains electron. These are the electrons in the conduction band. These are the holes in the valence band. And this is the band diagram of a PN junction diode. Now let us see what happens when such a PN junction is formed and an equilibrium is established. What is the situation of a PN junction at equilibrium? The higher concentration of holes on p side and electrons on n side cause the diffusion of charge carriers at the junction. So the diffusion happens across the junction because one side is p-type and other side is n-type. So what happens during diffusion? During diffusion, these carriers will meet and they recombine, and as a result, we will get a region which does not contain mobile charge carriers. That is, we have a region which is devoid of or depleted of mobile charge carriers, and such a region is called a depletion region. And in that depletion region, a built-in potential is developed, and because of that built-in potential, further diffusion is prevented. This built-in potential prevent further diffusion across the junction. This is the depletion region that is formed during equilibrium. We can see that there is a slightly negative and positive charge at the junction. This region is p-type and this region is n-type. And when the PN junction is formed, there is a diffusion of electron from n to p side, and also there is a diffusion of holes from p to n side. And after some time, a depletion region is established and a built-in potential is created which prevent further diffusion. So an equilibrium is established. This is the band diagram of a PN junction at equilibrium. We can clearly see there is a band bending happens at the equilibrium, and EV0 is the built-in potential. Consider a PN junction under reverse biased configuration. Consider a PN junction under reverse biased configuration. For this configuration, connect positive side of the battery. Connect positive side of the battery to N region and connect negative side of the battery to P region. Now the resulting configuration is the reverse biased configuration. Now we can see that the width of the depletion region is increased under this configuration. That is, the depletion region is widened. Now what is the consequence of that? The potential difference across the junction, is increased because the depletion layer width is increased. Now as a result, only few carriers have enough energy to cross the potential barrier. Carriers means it can be electrons and holes. Few carriers have enough energy to cross the potential barrier. And we can say that as a result, the current flow is very much reduced. Now, let us consider the PN junction under forward biased configuration. Consider a PN junction diode under forward biased configuration. Now, for this configuration, connect positive side of the battery to P region. Connect the positive side of the battery to P region and connect the negative side of the battery to N region. The resulting configuration is the forward biased configuration, and you can see that the width of the depletion region is very much lowered, or the depletion region is narrowed. The width of the depletion region is reduced means the depletion region is narrowed, and as a consequence, that potential difference across the junction, that is the built-in potential difference across the junction, decreased. The potential difference across the junction is reduced. And we can see that due to this, the carriers flow easily across the junction because a very narrow depletion region, the carriers can easily cross the junction. The electrons and hole can easily cross the junction. And as a result, the current flows easily. So we can conclude that the diode allows current to flow freely in one direction. That is, under forward biased configuration, the diode allows currents to flow freely, but prevent current flow in opposite direction. That is, when the diode is under reverse biased condition, it will not allow the current to flow through it. Thus, we can see that the semiconductor diode is acting as a one-way valve. Now let us write the mathematical relationship between current and voltage in a diode. What is the mathematical relation connecting current and voltage in a diode? Now suppose the diode is under forward biased condition. Now under forward biased condition, the current due to majority carriers, from N to P side, it is actually electrons. The current due to majority carriers means here it is electron, is given by the expression is given by I is equal to I0 e raised to EVB by KT, where VB is the applied battery voltage, KB is nothing but the Boltzmann constant, and T is the temperature. So I is equal to I0 e raised to EVB by KT is the expression for the current under forward biased condition. Here I0 is the reverse saturation current. Now, what is the expression for net current in the diode? I net is given by I0 e raised to EVB by KT minus I0, where minus I0 is the current due to minority carriers. So in a diode, there is current due to majority carriers and also the current due to minority carriers. Here minus I0 is the current due to minority carriers. So we have a net current. So you can write the net current as I0 e raised to EVB by KT. Now let us put a bracket, then minus 1. So this is the expression for the net current that is flowing through the diode. The diagram shows a forward biased condition and reverse biased condition. In forward bias, the current increases exponentially. Also, you have minus I0, it is a reverse saturation current. The breakdown voltage is also shown under reverse biased configuration. Now let us discuss a problem. The question is, under forward biased condition, the diode current is 4.5 into 10 raised to minus 1 ampere. It is actually the net current. The reverse saturation current is 2.2 into 10 raised to minus 8 ampere. That is actually I0. The battery voltage is 0.12 volt. This is VB, that is 0.12 volt. What is the diode temperature? From the given data, we have to calculate the temperature of the diode. This is the question. So first let us write the expression for the net current. We have the net current I net is equal to I0 e raised to EVB by KT minus 1, where I net, it is given in the question as 4.5 into 10 raised to minus 1 ampere. The reverse saturation current I0 is equal to 2.2 into 10 raised to minus 8 ampere. The battery voltage VB is equal to 0.12 volt. Now let us separate e raised to EVB by KT from that equation. For that purpose, let us divide I net by I0, and that is equal to 4.5 into 10 raised to minus 1 divided by 2.2 into 10 raised to minus 8, and that is equal to 2.05 into 10 raised to 7. Now we have e raised to EVB by KT, that is equal to I net by I0 plus 1, and that is approximately equal to I net by I0, and that is equal to 2.05 into 10 raised to 7. The Boltzmann constant, the value of the Boltzmann constant is 1.38 into 10 raised to minus 23 meter square kilogram second raised to minus 2 Kelvin raised to minus 1. Now, to find out the diode temperature, let us take the natural logarithm on both sides of the equation. That is ln e raised to EVB by KT, and that is equal to ln 2.05 into 10 raised to 7. On solving, we have EVB by KT, that is equal to ln 2.05 into 10 raised to 7. Now let us solve the equation to find out the temperature. Now the temperature T is equal to EVB by KB ln 2.05 into 10 raised to 7. Now let us substitute the value of E, 1.6 into 10 raised to minus 19 into 0.12 divided by 1.38 into 10 raised to minus 23 into ln 2.05 into 10 raised to 7. On solving, we get the diode temperature T as 82.64 Kelvin.